Hi, I'm Paul Anderson, Field Application Engineer with Omron Automation, and today I'd like to talk to you about motion sizing. Motion sizing doesn't need to be difficult, but it does need to be correct. And using the motor sizing tool from Omron Automation makes it easy to get great results. And there are really only 3 steps that are required. Build your mechanical system, define your motion profile, and then select the best motor for the application. Let's take a look. After starting a new project, and I recommend using the full project instead of a light project, I can go in and I can add project description information and also machine description information. Next, I'll go into my list of axes, and I could add additional axes here, but for this example, I'll keep it simple with a single axis, but I will change the type of axis to a ball screw. Now, if I open up that axis, I can simply drag and drop mechanical components from the toolbox on the right if I wanted to change my mechanical system. So in this example, I have a motor going to a gearbox, which is then mated to a ball screw carrying the load. The last element in the chain is the motion profile, and that's going to define the motion of the load to which it's connected. So now with all of the elements in my system, let me go in and define the mechanical properties of each element. I'll start with a 3-to-1 gearbox ratio, and I can enter that by entering 3-to-1 in terms of the motor to load revolutions. And if I wanted to, I could also add additional information like inertia and efficiency. For the ball screw, I'll use a 20mm pitch, and I'll leave the inertia blank for now. But what I will do is I'll add the angle to -90 degrees to indicate that it's actually going to be a vertical axis. For my load, I'll enter 40 kilograms. With the mechanical system all defined, now let's go ahead and build a motion profile. To build my profile, I add elements in the profile editor by simply clicking on Add Instruction. And then I can either add compound elements like trapezoidal and triangle moves, or I could build a profile using single elements like ramp and constant. But in this case, I'm going to stick with trapezoidal moves. The move out will be 305 millimeters, and the motion will need to be completed in 1 second. Then when I am there, I will have a 2-second dwell time because of whatever process is required on the machine. Next, I'm going to add another trapezoidal move for the return move. Now, because I'm returning back to my original position, my move distance will actually be negative 305 millimeters, showing that I'm going back in the opposite direction. I'll set my move time to 1 second, but in this case, I only need a dwell time of 1 second. Now, if I look a little further below, the profile editor actually gives me various graphs to confirm that the profile I've entered is correct, and then I know I'm ready to move on and my motion profile is complete. Now, this is a relatively simple move, but even with complex cams, entering a motion profile is actually pretty straightforward. I can build a cam profile in Sysmac Studio, and then in the Multiview Explorer, I can right-click on the cam name and select Export Cam to a CSV. Then back in the motor sizing tool, in the profile editor, I can add an instruction for Import Cam as the element. Then I simply search for and select my exported CSV file, import it, and now my cam data is pulled into my motion profile. But for now, let's just keep it simple with the original trapezoidal profile. So I have my mechanical system defined, I've entered my profile, and now my last step is to simply select the best motor for the application. Now in the motor table, I can filter my results down to a particular product family, voltage range, and even more. I can decide the safety factor percentage that I want to use against all the various sizing criteria. And then lastly, I can ask to either see all allowable solutions, or better yet, just ask to see the most optimal solution. Once my motor is selected, the table to the left then shows the various sizing criteria. Column 1 shows the application requirements at the end of the motor shaft, whereas column 2 shows the results with the motor inertia added in. And then the column to the right in column 4 shows the percentage of max rating for each of these criteria based on the motor selected. Now, since I need a regen resistor for this application, the regeneration resistor tab also tells me how much regeneration power I need to have, and it gives me the allowable regeneration resistance for the selected motor and drive. And now that my axis is sized, there are a few different things I could do from here. I could add another axis to the application if this was a multi-axis application. I could print a report that's going to provide me all the detailed bill of material information, including motor and drive part numbers, plus my cable part numbers and any drive filter part numbers. Or lastly, I can actually export a file out of the sizing tool that I can then import into Sysmac Studio to begin setting up my project. In my Sysmac Studio project, I'll go up to the Tools menu and then select to import the motor sizing tool results. I'll locate my file, bring it into the project, and then that will add the servo drive to the EtherCAT map. It will create a motion axis, and then if I go into the motion axis, it even sets up the proper conversion data for the right user units. So in addition to making it really easy to get great sizing results, the motor sizing tool makes it easy to get a bill of material and to get your Sysmac project up and going. So if you have more questions or would like to download the motor sizing tool, go to automation.omron.com or contact your local motion solutions engineer to get a deeper dive into the motor sizing tool.